Okay, so welcome everyone. Thanks for coming, both here and remotely. Today's lecture is an example of how the Hilbert scheme of the affine plane can be used to make connections with representation theory. And I'm going to start with the representation theory part of things. So I want to start, in fact, in the 19th century with the classical results of Klein, who classified I guess I'll say non-trivial finite subgroups of SL2 up to conjugacy in the group SL2, and showed that there were two infinite families and three exceptions. There are the cyclic groups, which I write as Cm for m greater than or equal to 2. So these are cyclic of order m, and you can choose a particular representative of the conjugacy class of cyclic subgroups and say that this is the subgroup consisting of all diagonal matrices where zeta is an nth root of 1. And then there are the binary dihedral groups. Which I'll call dm for m greater than or equal to 2. This is a group of order 4m, and to write down a particular representative of the conjugacy class, you can take the group generated by, I guess it's actually C2m, and the matrix 0, minus 1, 1, 0, like that. So this diagonal cyclic subgroup here, except with 2m instead of m, and take that matrix as well, they'll generate a group of order 4m, and that's called the binary dihedral group. So, for instance, the first of these is D2, which is the quaternion group. So that's generated by the matrix I0, 0, minus I, that matrix. So in terms of quaternions, this is the element which you would want to call I, and this is the element you would want to call J, and they generate the familiar 8-element quaternion group. And so there are those two infinite families, and then there are three other examples: the binary tetrahedral, octahedral, and icosahedral groups.
I was just going to ask a very simple-minded thing. If you generate with Cm instead of C2m, what happens?
Oh, Josh was asking, sorry, I'll go back to the previous board to this question. Josh was asking about what happens if you replace this m with 2m with an m. So the point is that if m is odd, then if you had a Cm here, it wouldn't make any difference because the square of this matrix is minus the identity. So if m was odd and you also had minus the identity, then your Cm would become would go up to C2m automatically. And otherwise, if m is even, then then replacing this, changing this from 2m to m would give you the one with m over 2. Does that answer the question? I mean, there is some, yeah, there is a reason for it if you think about these groups. So the three others are the binary tetrahedral, octahedral, and icosahedral groups. So I won't really be referring to them during the lecture, but let's say they're called T, O, and I, and T has order 24, O has order 48, and I has order 120. There's some nice finite subgroups of SL2. The reason for the names is that these are related to the rotation groups of these platonic solids under the 2-to-1 covering map from SU2 to SO3. So this is one way to classify the finite subgroups of SL2C. Is to firstly show that any finite subgroup is conjugate to a subgroup of the special unitary group SU2. And then, so then its image is a finite subgroup of the group of rotations in 3-dimensional space. And you can classify those by considering their action on the sphere and showing that they have to be a rotation group of one of the platonic solids, or a dihedral rotation group, which is preserving a planar regular polygon, or a cyclic group. And so you get this classification in that way. So I'm not going to go further into this because it's not relevant for today's talk. It just explains why these groups are called what they're called, and sort of explains why there is a finite number of these exceptions that's somehow related to the fact that there's a finite number of platonic solids. Okay, so at various points in the 20th century, people realized that this classification of finite subgroups of SL2 is an example of an ADE-Dinkin classification, that there should be some relationship between this list and other well-known lists in Lie theory, like the classification of simple Lie algebras. And there are two ways to think of this as an ADE classification that I want to speak about. And I'll start with the one which is actually historically second, which is the so-called McKay correspondence. So McKay noticed that if gamma is a non-trivial finite subgroup of SL2C, you can define an affine Dinkin diagram from gamma in the following way. You define what's called the McKay graph delta tilde gamma. As follows. So the vertices are going to be, well, I'll just say that the vertices are numbers 0 up to L, and these are meant to index the irreducible representations of gamma. So I'll call the irreducible representations R0, R1 up to RL, following Nakajima's notation. And the edges in the graph tell you what happens when you tensor representations by the natural 2-dimensional representation of SL2. So I'm going to have to go back over to the other board. So if you let Q be the 2-dimensional representation of gamma coming from the fact that gamma is a subgroup of SL2, so the representation homomorphism is the inclusion of gamma in SL2C. So Q is C2, just regarded as a representation of gamma in this way. So in fact, for most of the types of finite subgroups that I wrote down, Q will be one of the irreducible representations, but not in the cyclic case. So Q is actually one of the RIs unless gamma is cyclic, in which case Q is reducible. In that case, of course, if the group is abelian, all the irreducible representations are one-dimensional. Gamma is the direct sum of two of them. And Q is the direct sum of two of them. So the definition of the McKay graph says that the number of edges between vertices I and J in delta tilde gamma is the multiplicity of Rj in Q tensor Ri. And so you take the irreducible representation Ri, tensor it with this two-dimensional representation Q, and then decompose that as a direct sum of irreducible representations. And so Rj will appear in there, possibly with a non-zero multiplicity. And if it does, you draw an edge between vertices I and J. And if there's a multiplicity greater than one, then you want to draw multiple edges. So it's actually a multi-graph in theory, although it turns out to be in almost all cases a single graph. And you can see, for instance, that this definition is symmetric in I and J. So this equals the multiplicity of I in Q tensor Rj because Q is a self-dual representation. Because the gamma is a subgroup of SL2, not just GL2. So the determinant gives you a skew symmetric pairing on Q, which is invariant for the group gamma. So Q is isomorphic to its dual, which you can easily see means that the multiplicities are the same if you reverse I and J. So, I mean, this looks like some abstract representation theoretic definition. It's slightly used the fact that gamma is a finite subgroup of SL2. So it's used the fact that it's a subgroup of SL2 here to know that it's an undirected graph, not a directed graph. And the surprising thing is that what you get out of this when you do actually plug in the list of Klein's list of finite subgroups of SL2C is exactly the affine Decker diagrams of the simply laced ones, the ones that type ADE. So McKay's observation in his famous paper has two parts. The first part is that delta gamma tilde is a simply laced affine Decker diagram. That is, it's one of the following graphs. It's so A1 tilde looks a bit slightly different from the other ones, so I'll draw it separately. So A1 tilde is the graph with two vertices 0 and 1 and two edges between them. A L tilde for L greater than or equal to 2 is the cyclic graph with L vertices. D L tilde for L greater than or equal to 4 is the graph with which looks like this. Minus 2. And then there are the graphs E6 tilde, E7 tilde, and E8 tilde. And I might just draw E8 tilde because the exact shape of these type E graphs is not going to play much role in what I say later on. So E8 tilde is the graph which looks like this. 3, 4, 5, 6, 7, 8, 9. So in the Bourbaki numbering, that would be 0, that's 1, that's 2, 3, 4, 5, 6, 7, 8. So if you look up the character table of the binary icosahedral group and use that to compute multiplicities in tensor products, you'll find that when you take the, I should have said actually that the numbering is always so that R0 is the trivial representation. So the trivial representation of the binary icosahedral group is over here. When you tensor that with Q, since this is not cyclic, you will get another irreducible representation. So Q for the binary icosahedral group is R8. So you draw an edge between the 0 and the 8 vertices. Then when you tensor Q with itself, this graph is saying that what you'll get is another now 3-dimensional irreducible R7, and the direct sum of that and the trivial representation R0. So the vertex 8 is joined to vertices 7 and 0. And then if you tensor Q with this new R7, you'll get a direct sum of R6 and R8. And eventually it carries on having 2 components like that until you get to this point. When you tensor R4 with Q, you get the direct sum of these 3 irreducible representations. So one thing you can see from this is that there has to be a relationship between the dimensions of all of these irreducible representations. You can work out the dimensions if you start from the knowledge that the, I'm not sure that that color is actually going to be all that visible for the people watching remotely. So I'll put dimensions in a square box like this. So we start here with a 1-dimensional representation, the trivial representation. Tensoring that with Q, we get this one. So that's 2-dimensional. Q times Q is meant to be the sum of these 2. So this must be 3-dimensional. So tensoring this with Q, we get something 6-dimensional. So that's meant to be the sum of this and this. So that must be 4. Similarly, that must be 5-dimensional. And this must be 6-dimensional. And now you can see that this representation tensor Q is 12-dimensional. So the sum of those 2 must be 7. But also this tensor Q is meant to be isomorphic to this one. So this one must be 3-dimensional. This one must be 4-dimensional. And this one must be 2-dimensional. So you end up with a labeling of your graph by positive integers, which has the property that twice the label at any vertex is the sum of the adjacent labels. And it turns out it's not particularly hard to classify the graphs with that property and show that they are in fact the affine, the simply laced affine Dinkin diagrams. The graphs which have a labeling by positive integers with that property. So the first part of McKay's observation is not tremendously surprising if you know that graph theoretic interpretation of these graphs. But what's really quite remarkable is that this is actually a correspondence, that it gives you a bijection from the set of non-trivial finite subgroups of SL2 taken up to conjugacy, and the set of simply laced affine Dinkin diagrams. So it's clear that you have a map from left to right. That's the map given by the McKay graph construction, taking gamma to delta tilde gamma. But it's amazing that it's a bijection. I mean, this says, for instance, that every one of these graphs does appear as the graph arising from a finite subgroup of SL2C. So In particular, if you didn't know the existence of the binary icosahedral group before, this is saying that the mere fact that there is an affine Dinker diagram of type E8 tilde, which has this where you can put these positive labels on the vertices and have that property. So if all you knew was that, it's a much stronger statement to say that there actually is a finite subgroup of SL2 whose irreducible representations have these dimensions, such that this graph records the tensor product decompositions when you tensor with the standard two-dimensional representation. And this is also saying that this map is injective, that you can't have two different conjugacy classes which happen to have the same McKay graph. So neither of those things is particularly obvious. And McKay's just observed that this follows from the known classifications. If you just work out what the McKay graph is for every one of the groups on Klein's list, then you get exactly these diagrams once each. So the way it matches up is that the cyclic groups correspond to the affine Dinker diagrams of type A. So actually CM corresponds to a m-1 tilde. The binary dihedral groups that I wrote before, DM, they correspond to the affine Dinker diagrams of type D. So the binary dihedral group DM corresponds to the affine Dinker diagram D m+2 tilde. And then the other three, the tetrahedral, octahedral, and icosahedral groups correspond to these E6, E7, and E8. So you just get each one once each. Okay. So are there any questions about that before I move on to the geometric way of thinking about this?
Could you use this to give a new proof that there are only finitely many Platonic solids?
Josh is asking if you can use this to give a new proof that there are only finitely many Platonic solids. Well, I mean, so in order to do that, you would need a proof of the statement that this is a bijection which did not rely on just matching up classifications on either side. If you wanted to do that, and I'm not saying that it would necessarily be worth doing that, but if you wanted to, you would certainly need a better understanding of why there's a bijection than just saying we've classified both sides and they line up. So that has motivated various people to try and understand this bijection in more conceptual terms, in particular to think about how you can conceptualize the inverse, starting with an affine Dinker diagram like this E8 tilde diagram here. You can easily work out what the dimensions of the irreducibles of the corresponding group will have to be, but how do you actually construct the group? So that's an interesting topic, and I guess what I'm saying today sort of contributes to that a little bit. At least it gives us a different way of understanding this bijection, which does, maybe it doesn't really advance you any further in understanding the inverse, but at least it gives better understanding of the bijection. Okay, so what I want to explain now is a geometric way of constructing this bijection, or the slight twist is that it doesn't actually result in the affine Dinker diagrams, it results in the finite type Dinker diagrams. So it's slightly different, but in the same spirit. And this doesn't have a name like McKay correspondence, but it probably should be called the Duval correspondence or the Duval-Klein correspondence, or to credit various singularity theorists who realized that this was an ADE classification many decades before McKay's paper. So this works as follows. So the geometric approach is to start with your finite subgroup of SL2, and consider the quotient of the two-dimensional representation, which I was calling Q, by the action of gamma as an algebraic variety. So I think I'll call this Y gamma. So I mean that Q is just C2 regarded as a representation of gamma. So in particular, it's just two-dimensional affine space with an action of this group gamma. We can take its quotient in the sense described before. So this means that Y gamma, by definition, is the affine variety with coordinate algebra where you take the coordinate algebra of the affine plane, C, Z1, Z2, and inside there look at the polynomials which are invariant under the action of gamma. And so this is now a new commutative C algebra, and the affine variety corresponding to this is the one we're calling Y gamma. So this is this quotient is, on the one hand, a relatively easy one to think about because we're quotienting by a finite group. On the other hand, it's not a free action on the whole of Q, like some of the quotients that occurred in previous lectures. And in fact, what's easy to see is that the gamma action is free if you remove the origin. This is just because if lowercase gamma is a matrix of finite order, and V is a non-zero fixed vector, then since it's finite order, it's diagonalizable. And since it has a fixed vector, one of its eigenvalues is is 1. And the other eigenvalue is alpha. And then, so if you also know that the determinant of gamma is 1, then alpha has to be 1 as well. So gamma is the identity. So if you're talking about finite subgroups of SL2, they can't have non-zero fixed vectors. Non-trivial finite subgroups of SL2 can't have non-zero fixed vectors. So I left out the word non-trivial here earlier in the page. I should have said that, I suppose. Well, it wouldn't have mattered to this lemma, but it matters to what I'm about to say. This means that when you take the quotient, if you throw away the origin, this is a free quotient, and you, as we've seen in previous lectures, that means that you get something smooth. But if you include the origin, then you have a singularity at the origin. So these are what is called the Clonian singularities. So the result of this is that that quotient is smooth, but Y gamma as a whole has a singularity at 0. And Klein actually computed these invariant rings in each case, and found that they are always of quite a simple form. They have 3 generators which satisfy a single relation. So what that means is that the affine variety with this coordinate ring, y gamma, can be embedded inside A3, and it's a singular hypersurface. Well, a hypersurface in A3, which means it is a surface. It's a singular surface with an isolated singularity, with actually just one singular point. So it's nice to work out some the examples of the cyclic and binary dihedral group cases, which are not so hard. It's a little, you need to work a little harder to work out the invariant rings for the other 3 groups. But for the case where gamma is Cm, for instance, so remember this in our standard representative of the conjugacy class consists of just those diagonal matrices where the entries are m fruits of 1. So what polynomial functions are invariant under the action of diagonal matrices like that? It's easy enough to see that this algebra is generated by so one function which is invariant is Z1, Z2, because if you act by this matrix, then one of them will get scaled by zeta and the other will get scaled by zeta inverse. So Z1, Z2 is invariant. Also, Z1 to the m is invariant since you're scaling by an nth root of 1, and Z2 to the m is invariant. And if you call these generators x1, x2, and x3, then they satisfy the single relation that x1 to the m is x2 times x3. So this embedding in A3 realizes YCM as the singular surface in A3 defined by the single equation that x1 to the m is x2 times x3. Maybe I better say, for the benefit of those who may not know, how to calculate the singular locus of a hypersurface. That's a nice easy thing. If you have a hypersurface in affine space, just for simplicity, because those are the cases that I'll be looking at. So if Y is the set of points, well, maybe A1 up to AN in affine n space, where some particular polynomial vanishes. So F, just a polynomial in variables. Then the points in Y where Y is singular are exactly the ones So firstly, they have to be in y, so this polynomial has to vanish. But then it's exactly the ones where all the partial derivatives of the polynomial vanish as well. It's not hard to relate this condition to the definition of tangent space that I talked about a couple of weeks ago. So for instance, if in our example of Cm, if we have the polynomial is x1 to the m minus x2, x3, then the partial derivatives vanish only at the origin. So this you could compute if you didn't already know just from the equation that this is an isolated singularity. The only singular point is the origin. So a slightly harder exercise would be to work it out for the binary dihedral groups. So to show that if you use the explicit description of the binary dihedral group as a subgroup of SL2 that I gave at the start, you can write down some invariant polynomials. So now Z1 squared times Z2 squared will be invariant, and Z1 to the 2m plus Z2 to the 2m will be invariant, and with a little more thought, you can find a third invariant which is not generated by the first two. And if you call these x1, x2, and x3, then they satisfy the relation that for x1 to the m plus 1 equals x1, x2 squared plus x3 squared, or minus x3 squared. Can't read my writing, minus. Sorry, regular was oh, this is, sorry, yes. This is for gamma, the binary dihedral group Dn. Thanks. So, so Y gamma for the binary dihedral groups is the hypersurface in A3 given by this single equation here. I mean, once again, it's trivial to see that the only singular point is the origin. So you have this particular reasonably nice polynomial equation that you're studying the vanishing locus of. So I won't write down the equations for the other three groups, but you can find them on the Wikipedia page for Clonian Singularities, probably. So the reason that these are particularly nice singularities, as opposed to all the other, I mean, obviously you can write down lots and lots of equations like this, as long as you make the powers in these monomials high enough, then the only singular point will be at the origin. And the reason that these particular Kleinian singularities, as they're called, the Y gammas, are special, is that they turn out to be the only isolated surface singularities which are normal. So I just need to explain a little bit of the theory of normal varieties. This will be useful later in some of the proofs relating this to Hilbert schemes. So the special property of the Clonian singularities y gamma is that they are normal so what that means is, so this is the definition for an arbitrary irreducible variety. I think I only want to give the definition for affine varieties since that's the only case that I'm going to need, and then it makes it easier. So an irreducible affine variety Y is normal if its coordinate algebra is integrally closed in its field of fractions. So this is some integral domain because I said Y was irreducible. And so it's embedded inside its field of fractions. And integrally closed means that if you have some alpha in the field of fractions, which satisfies a monic polynomial, alpha m plus a1 alpha to the m minus 1, am, where these AIs are in the coordinate algebra, and this is 0, then alpha has to be in the coordinate algebra itself. So this looks like some slightly funny commutative algebra condition, but turns out to be quite a naturally arising condition when you start thinking about singularities. So the classic example of a non-normal singularity. Oh, so I should say, firstly, that it's a fact, essentially a commutative algebra theorem that all smooth what did I say? Irreducible affine varieties are normal. So if you, well, so the concept really becomes relevant when you're talking about singular varieties, and then some singularities are normal and some are not. So the classic example of a non-normal singularity would be the cusp singularity Y. So say x1, x2 and a2, such that x1 cubed equals x2 squared. So if you imagine just drawing the real points of this, if that's the x1 axis and it's the x2 axis, then the curve looks like this. I shouldn't have made that look as if it was turning up. Anyway, I haven't drawn that very well, but it comes to a singularity here at the origin. So this is so the coordinate algebra is the quotient of the polynomial ring in two variables by the ideal generated by this relation. And it's easy to see that that's isomorphic to the subalgebra of the polynomial ring in one variable generated by the square and the cube of that variable, where you send x1 to t squared and x2 to t cubed. So the field of fractions is the ring of is the field of rational functions in one variable, and the t that's missing from this coordinate algebra is integral over this coordinate algebra, but not contained inside it. So t is integral over cy. So this variety fails the normality condition of being integrally closed in its field of fractions. And what does this mean? It means that so in this example, it allows you to have a bijective morphism to this variety, which is not an isomorphism, exactly given by this t. So notice that the morphism from the affine line to this z, which sends t to t squared t cubed, this is a bijective morphism which is not an isomorphism. Oh, sorry, thanks. So this is the sort of thing that can happen when you have non-normal varieties around. I mean, this is a bijection on the level of C points. It's a for every complex point of the variety Y, there's a unique. I mean, if you write x1 and x2, there's a unique t for which x1 is t squared and x2 is t cubed. But the map which takes x1 and x2 to that t is not a morphism of varieties. I mean, the map is a rational map in the other direction. It's sending, what you want to do is send x1, x2 to x2 over x1. So the inverse exists as a rational function, but it's not a morphism. I mean, it's not defined at the origin. So that formula is not defined at the origin, but nevertheless, the correct answer is 0 at the origin. Yeah, so the nice fact that will be useful is that if you have a bijective morphism of varieties, and if the target is normal, then actually the inverse map is a morphism. So F is an isomorphism of varieties. So that illustrates why one way in which normal varieties are nicer. And the proposition is that the Clonian singularities are normal. For all gamma n SL2C. And in fact, this is true for quotients of any normal variety by a finite group. So what you need to show is that CZ1, Z2, gamma, the gamma invariant polynomial ring, is integrally closed in its field of fractions. Its field of fractions, it's easy to see, is the gamma invariant subfield of the field of rational functions in these two variables. So you have to imagine a gamma invariant rational function which satisfies an integer polynomial with coefficients here, and you want to show that it actually lies in here. I think I might have to skip the rest of the proof. So the idea is just you use the fact that gamma is finite by so your putative element here clearly has to lie in the polynomial ring from the fact that the polynomial ring itself is integrally closed. So the question is just whether it's okay. Sorry. So I begged the question by writing down this statement. So this is not the hard part. The part which requires thought is to show that this gamma invariant subfield is the field of fractions of this. So it's obvious that the field of fractions of this is contained in this, but you need to be able to show that if you have a rational function which is gamma invariant, then you can write it as a quotient of two gamma invariant things. And that's where you use the finiteness of gamma. There's a standard trick where you multiply the numerator by all its translates under gamma to produce something gamma invariant. Okay, sorry, I've got that the wrong way around. So what you, the main part is to show that the field of fractions of the gamma invariant polynomials is the gamma invariant rational functions. Okay, I better take a break at this point and see if I can think of something more coherent to say about this, or else I'll just plow on. Okay, so I need to recall another standard definition in the study of singular varieties, which is the definition of resolution of singularities. So if Y is an irreducible variety, resolution of singularities Y is a morphism of varieties from some other variety X to Y, such that one X is smooth and also irreducible. Two, pi is proper. Now, I don't want to get into the general definition of proper, but in the cases that we will see, it's actually going to be projective, which is a special kind of proper morphism. So what projective means is that pi factors through closed embedding of X in the product of Y with some projective space. PM, and then just projecting onto the y factor. And the third property that you need is that pi is birational, which means that it's an isomorphism on some open subsets of varieties. So there is some non-empty, of course. And I mean open in the Zariski sense. So in fact, it's non-empty since Y is irreducibly dense. So some open set inside Y such that if you restrict pi to the pre-image of U, which will be then an open subset of X, that gives you an isomorphism between this open subset of X and this open subset of Y. So we think of the smooth variety X, which has no singularities, as resolving the singularities of the variety Y. And to go from Y to X, we've changed things a little bit. They're isomorphic on open dense subsets, but in the parts which are not in this open subset U, we could have changed what was in Y quite a bit. So this U is necessarily going to be contained in the regular locus of Y. So if you throw away the singular points of Y, U will live inside there because it's isomorphic to an open subset of a smooth thing. So U itself is smooth. Some definitions of resolution of singularities would actually force, would actually have this condition written with U being the whole of the regular locus, so that you require that you actually haven't changed anything outside the singular points. But I find in practice it's better just to say it like this and allow the possibility that you've done some seemingly unnecessary things. You've made some changes to points which weren't singular already. So some examples are, well, okay, before I even write that out, rub out that line. That's an example. So example one is the this bijective morphism that we had before. So this it's not an isomorphism as we saw, but it would be an isomorphism if you removed the singular point from Y and the point 0 from A1. So it's not an isomorphism, but it induces an isomorphism between this open set of A1 and the corresponding open set Y. So that satisfies these conditions. Is not, well, sorry. Yes, it is. Yes, it is projective. So I can write this. Probably going to get this wrong, but I'm pretty sure I can embed this in A1 cross, sorry, in Y cross P1 in a way that will project Y. So let me see, I need to send T to T squared, C cubed, and okay. So what I want to say is that A1 is isomorphic to the points x1, x2, alpha, beta in y cross P1, such that, so we've got the equation for y, which was x1 cubed equals x2 squared. And we've got the equation that beta beta x1 equals alpha x2. No, but I don't want there to be a whole. I don't want there to be a whole P1 above above the 0 point. So what should I be doing? I should be putting an extra condition that at 0, 0 forces say alpha to be 0. Sorry, well, I'm probably going to have to abandon this here. I am morally convinced that I can put some extra condition here that some extra closed condition that will produce something which is actually isomorphic to A1, and then yeah, I wasn't prepared for for that one. So a non-example is the quotient map from A2 to Y gamma. So this is not a resolution because it fails condition 3. So generically, of course, the inverse image of a point here, if you're away from the singularity, is a gamma orbit of points in here. So it's not one-to-one generically, like a resolution of singularities has to be. So it's non-example 2. So example 3. There's one of the Y gammas where many of the members of the audience will know a resolution of singularities, which is when gamma is C2. So remember why C2 is the singular surface in A3 defined by the equation x1 squared equals x2 x3. And you can, that occurs naturally in Lie theory as the set of nilpotent 2x2 matrices. So this is A inside, say, SL2, such that, well, what not to say 2x2 matrices of whose trace and determinant are both 0. Because you can send the triple x1, x2, x3 to the matrix x1, x2, x3, negative x1. And then the determinant 0 condition becomes exactly this equation, or maybe I need a sign, x1 minus x2. Yes, so Kailan's made a comment that in the previous example, the map is certainly proper because it's a finite morphism, which is true, yes. And the reason I was immediately convinced that I would be able to write down a diagram realizing it was a projective morphism is that you have to go a lot further afield than that to find examples of proper morphisms that are not projective. Well, anyway, yes, so the comment is definitely true. So getting back to this example, unless I made a sign mistake, that's every nilpotent 2 by 2 matrix is of that form for x1, x2, x3, satisfying that equation. So the set of the nilpotent cone in 2 by 2 matrices has a well-known resolution of singularities called the Springer resolution. Where you take for your x the set of pairs of a nilpotent matrix, so in other words, a triple like this, and a flag that the nilpotent matrix stabilizes. In this case, we're in a 2-dimensional space, so flag just means a line in that 2-dimensional space, or in other words, a point in P1. So you can write it as alpha 1, alpha 2 in homogeneous coordinates. And the condition for the nilpotent matrix to stabilize the flag turns out to be the condition that alpha 1, I'm probably going to get this wrong too, unless I consult the notes. Alpha 1, x1, minus alpha 2, x2 equals 0. So I'm actually just taking this 2 by 2 matrix and multiplying on the column vector alpha 1, alpha 2 on the right, and I want that to give you the 0 vector. So the other condition is alpha 1, x3 minus alpha 2, x1 equals 0. Okay, and then you map this to YC2 by forgetting about this alpha 1, alpha 2 part. So this is manifestly a projective morphism because I've factored it through the product of Y and a projective space and a closed embedding there defined by these closed conditions. And it's easy to see that it's an isomorphism away from the singular point. That is to say, if you have a non-zero nilpotent 2 by 2 matrix, there's a unique line that it stabilizes, which is its image and its kernel. And well, it's not just unique, but the map which takes you from the matrix to its kernel as a point in P1 is a morphism of varieties. Yes, and this X is smooth because actually you can, X doesn't change if you replace this with just A3. Because these conditions, since alpha 1 and alpha 2 are not both 0, these conditions actually force the determinant of this matrix to be 0. So they force the condition that we had before. And if you write it that way, then it's just a closed subvariety of this product of A3 and P1 defined by these linear equations. It's very easy to check that that's smooth. So the picture of this YC2 is some sort of cone. At least if you took the real points of this variety, it would actually be a genuine cone. So picture this YC2 as something like this. A singular surface with singularity at the origin. And when you construct this Springer resolution, you're blowing up the singularity at the origin and getting some smooth thing like this. Where now the fiber over the origin is a P1 here inside your variety X. Okay. So there's a similar Springer resolution for the nilpotent cone in any simple Lie algebra, but unfortunately, our story today departs from that at this point. The other Clonian singularities are not examples of nilpotent cones like that. What we're going to look at is the so-called minimal resolutions of the Clonian singularities. And this is these are the facts that were discovered by algebraic geometers in the first half of the 20th century about resolutions of Clonian singularities. That Y gamma has a unique minimal resolution of singularities. So it's minimal in the sense that other resolutions of singularities factor through this. So this resolution has made the least change possible to Y gamma to make it, to give you something smooth. And it's an isomorphism away from the an isomorphism over the regular locus. I can't remember what the singular point in Y gamma was called, but it's some zero in some sense. And so the only part that's changed is the singular point. So the exceptional locus, as it's called, E gamma, the fiber over the singular point here, so some closed subvariety of X gamma, is a connected union of projective lines. So in the example of C2, there was just one projective line in the fiber. But if you look at the other Kleinian singularities and use the techniques of singularity theory, people found that the what you get is always connected. That's actually can be proved using the general result known as Zariski's main theorem and the fact that Y gamma is normal. And every irreducible component of this exceptional locus is a projective line. So the information in there is really just about which projective lines intersect other ones, which other ones. And this is Duval's observation, which you could call the Duval correspondence. So if you let delta gamma be the graph with vertices 1 up to L, where these are indexes for the irreducible components of E gamma. So these various projective lines, and you join vertices I and j if the corresponding irreducible components intersect. Then the observation was that what you get is a finite Dinkin diagram of type ADE. And what's more, this gives you a bijection again between the conjugacy classes of non-trivial finite subgroups of SL2. So this is gamma as before, up to conjugacy, is in bijection with the simply laced finite Dinkin diagrams in this way. So this was the original way of seeing the classification of, well, I think it was the original way of seeing the classification of finite subgroups of SL2 as an ADE classification, that you can produce the finite Dinkin diagrams by considering the minimal resolution of the Clonian singularity and looking at the intersection pattern of the irreducible components of the zero fiber. So what's amazing, well, I mean, that's perhaps already just as surprising as the McKay correspondence. But what's also surprising is that the two correspondences are the same in the sense that the finite Dinkin diagram that you get from the geometric definition is the graph obtained by deleting the zero vertex in the affine Dinkin diagram that you get from the representation theoretic definition. So it's obtained from delta tilde gamma by deleting the zero vertex. So this is saying there's some relationship between the geometry of this minimal resolution X gamma and the representation theory of gamma. The McKay graph, delta gamma tilde, is obtained as defined purely in terms of representations of gamma. This Duval graph, if you want to call it that, delta gamma is obtained purely in terms of the geometry of the resolution of singularities of the Clonian singularity obtained by quotienting affine 2 space by gamma. And yet they give you the same graph, except that you have to delete the zero vertex in the affine Dinkin diagram to get the finite Dinkin diagram. But otherwise, it's the same correspondence. So somehow you could say that this variety knows something about the representation theory of the group gamma. Or I suppose if you could think of it the other way and say that the representation theory of gamma knows something about the geometry of Clonian singularities. So it's this part that I want to explain. So what I want to explain, and this may in fact end up, probably will end up going into another lecture, is how you can construct this minimal resolution X gamma using the Hilbert scheme that we've been studying so far. And see why you would expect it to relate to representations of gamma. So are there any questions? Yeah, so Kevin in the room is asking which Hilbert scheme. And so this is sort of given away by the next point. So the starting point for why there should be a relationship between X gamma and Hilbert schemes at all is that if you think about Y gamma, so this was the quotient variety of the two-dimensional vector space Q by gamma. So a point here is a gamma orbit in Q. So in particular, you can think of this as a special kind of unordered n tuple of points in Q, where n is the order of gamma. Maybe it'd be best if I actually write stronger statements which are true only away from the singularity first. So so a non-singular point in Y gamma is a gamma orbit in Q with the origin removed. And on the complement of the origin, the gamma action is free. So a gamma orbit consists of n different points if n is the order of gamma. So that's a special kind of unordered n tuple of points in Q. Points in Q with the origin removed. So it's a point of the nth symmetric power of Q with the origin removed. So when we're looking at these quotient varieties Y gamma, the points are collections of points. I mean, they're orbits. And the size of the collections of points is the order of gamma. So the Hilbert scheme stuff we've been talking about is about finding nice ways to let collections of points coincide. And that's exactly what we want to do when we try to incorporate something else in addition, which replaces the singular point of Y gamma in a way that will make something smooth. What I claim is that, first of all, if you put back the singular point to get the whole of Y gamma, then that's exactly the gamma fixed locus inside the nth symmetric power of Q. So it's maybe a bit fussy to keep writing this as Q. It's just the affine plane, but you write it as Q when you have this particular representation of the group gamma in mind, and that's what defines the gamma action on the nth symmetric power. And I'm claiming that the gamma fixed points in the nth symmetric power of Q are exactly the n tuples that are just the orbits of gamma in Q. So this is not particularly hard as a consequence of the fact that it's a free action. So firstly, I'll just show that a bijection on the level of points so what does it mean to say that you have a gamma fixed point here? So if say square brackets for an unordered n tuple. So if this in the nth symmetric power of Q is the image of x1 up to xn in the normal nth power of Q. The symmetric power is just the quotient of the nth power by the action of the symmetric group Sn. So what does it mean for this to be gamma fixed? So that means for all elements of the group gamma, when you apply gamma to this unordered n tuple, you get the same unordered n tuple. So that doesn't mean that these are the same term by term. It means that gamma x1, well, this, the gamma xn is a reordering of x1 up to xn. And now, since the action away from 0 is free, so if any xi is non-zero, this condition forces the set of x1 up to xn to be the gamma orbit of xi. Because as soon as you have something non-zero, it's this condition will force all its translates under elements of gamma to be contained in the set still, and the size of the set is exactly the size that you expect that orbit to have. So either you have some non-zero component in which case you actually your unordered n tuple has to be a gamma orbit, or if all the components are 0, then you correspond to the 0 orbit in Y gamma. So at the level of points, it's a bijection. Then you just have to check that that you have, for instance, a closed embedding. That one of these maps is a morphism and a closed embedding or something, and then if it's a bijection of the level of points, it will be an isomorphism as well. So the easiest way to define to turn this correspondence into an actual morphism of varieties is to go think about the unquotiented level first. So I suppose you have to choose an ordering of the elements of gamma. Then you have a closed embedding of Q inside Q to the n, where you send a point x to its translates under the elements of gamma in this particular order. And yeah, I mean, it's very easy to see that that's a closed embedding if you think about the equations needed to define a tuple of that particular form. And I mean, one of these group elements will be the identity. So you will actually see x itself here as maybe the first component here. And then if so, this induces a closed embedding from the quotient by gamma here, if you to the quotient by Sn here. I think that's quickly. You just have to convince yourself that any so this is equivalent to saying that the map on coordinate algebras in the other direction is surjective. So here you have the Sn invariant polynomial functions on the direct sum of n copies of Q, and here you have the gamma invariant polynomial functions on Q. And so if you have any gamma invariant polynomial function on Q, you can just take that polynomial in each component of your direct sum, and that will give you an Sn invariant polynomial function on Qn, which maps to that one that you had. And that's the map on coordinate algebras, which is which relates to the map between these quotients induced by that map on the unquotiented level. So there's a few little things to check, but it's not tremendously hard. Kevin?
Yeah, well, I mean, you basically answered most of what I was about to ask. But I was going to say, we haven't, so far as I remember, really introduced symmetric power as a variety. So I would presumably just introduce a spec of invariant holomorphic.
Yeah, that's right. So Kevin's asking about the yeah, sure, maybe. So with the symmetric power that I defined in the first lecture was meant to be the quotient of the product of n copies of x by the action of Sn. So if x is affine, then this is affine, and its coordinate algebra is the Sn invariance in the coordinate algebra of the product of n copies of x, which is the nth tensor power of the coordinate algebra of x. So there's a definition of this as a variety. And so Kevin was asking whether we could do things in the framework of algebra rather than varieties. And up to this point we could, but the point now is that we want to bring back the, or we want to resolve the singularity. And that's necessarily going to involve non-affine varieties because, oh, for the proposition, yes. Yeah, you're right. This proposition is equivalent to a statement about the isomorphism between two commutative rings. The problem is that I have to move over to the other board, I guess, to answer this question. So the problem is it's easy to get a handle on the coordinate algebra of the symmetric power. It's just an invariant ring, as I said before. But then saying what the coordinate algebra is of this particular closed subvariety where you take the gamma fixed points is not so, well, I mean, I think that's where it helps to think about points rather than pure algebra is exactly this part of taking the gamma fixed points. So to say that the image of this closed embedding is exactly the gamma fixed points to the right-hand side. That's what was explained on this board. Yeah, so that's where I think it helps. Okay. All right, so just to wrap up, obviously I'm going to have to do most of the explanation in a future lecture. But the point now is that we know how to find smooth varieties that relate well to symmetric powers. So I haven't actually proved yet that in general the nth Hilbert scheme is a resolution of singularities of the nth symmetric power of a surface. But what is true here so in a later lecture, we will see we will find the minimal resolution as a closed subvariety of the gamma fixed points in the nth Hilbert scheme of Q. And then, so here we have the Hilbert morphism that takes a length n subscheme and produces a cycle. So this, we know this naturally maps to the gamma fixed points in the nth symmetric power. And we've just seen that that's isomorphic to Y gamma. And so the Hilbert morphism here is going to give us our resolution of singularities. So this will be a good thing to look at, because we've seen in the previous lectures that this Hilbert scheme is smooth, and it's a general fact that if you look at the fixed points of a finite group action on a smooth variety, then every connected component of that is smooth. So this might have multiple connected components. So you only actually want to look at one of the connected components, and that's the construction of the minimal resolution of Y gamma. Maybe I'll just spoil the later thing a bit. So actually, if you think in terms of ideals, X gamma is going to be the set of ideals of our polynomial ring, codimension-n as before, such that I is invariant under gamma. So that's just saying that you're in the fixed point set of the Hilbert scheme. And moreover, the extra condition you need to get the right connected component is that since I is gamma invariant, if you look at the n-dimensional quotient, this is now a representation of gamma. Sorry, I. So gamma acts on this n-dimensional space, and you require that this is isomorphic to the regular representation of gamma. So this particular subset of the nth Hilbert scheme is a very nice construction of the minimal resolution of the Clonian singularity. And now at least you're in the right ballpark that this is if you define it this way, this is a variety which clearly has something to do with representations of gamma. In fact, you've got a regular representation floating around, so all the irreducibles are in the picture somewhere. And now at least it's a step more plausible that the geometry of this variety has something to do with the McKay graph of gamma, because at least there's more representations of gamma involved. Okay, so that'll have to be in a later lecture, possibly 2 weeks' time, possibly after that. Thank you. Are there any questions?
I wonder why all graphs are almost the same.
Oh, so Gaston's asking why the two graphs are almost the same. So yeah, so this is what possibly I will eventually get up to. I mean, after proving that this is the minimal resolution, you then have the hope of looking at the geometry of X gamma, and it will turn out that you can construct various vector bundles on X gamma corresponding to the irreducible representations of gamma. And what happens is that those vector bundles form a basis for the K theory of X gamma. And as a consequence of that, the Duval graph can also be interpreted in terms of the K theory of X gamma, because the intersection of the P1s determines the intersection form on the second homology of X gamma. So there's then a relationship between the Duval graph, which is effectively telling you the intersection form on H2 X gamma with respect to one particular basis, and the McKay graph is effectively telling you the intersection form on the K theory of X gamma with respect to this basis given by vector bundles. So yes, hopefully we'll get up to that at some point.
At least we are going to understand the correspondence between the vertices.
Are we going to understand the correspondence between the vertices? You mean why?
Because I wonder if just the graph is the same as the other.
Yeah.
Each vertex is mapped to a special vertex.
Oh, I see what you're saying. Yes, okay, that's a good question. So is there actually a canonical way of saying that the that one particular irreducible component of E gamma, for instance, is the one that corresponds to this irreducible representation of gamma? I don't think that's actually true, because it feels to me like the symmetries are different in the two sorts of graphs. I mean, the finite Dynkin graph has a different symmetry group from the affine Dynkin graph, to make an obvious comment. And so, for instance,
maybe before it's about something.
I guess the question is, which node is left out? Is there a different interpretation for that representation that doesn't appear as a P1?
Well, I mean, it's the node you want to leave out of the affine Dynkin diagram is always the trivial representation, but there are a number of nodes which are equivalent under the graph, under the automorphism group of the graph to the node which is the trivial representation. Yeah, so there is a reason to why you leave out one of the nodes, and that's because there's a difference between K theory and H2. So that can be explained in geometric terms, that the trivial representation is somehow corresponding to the one-dimensional H0 of the space, and the rest are giving you a basis of H2. Yeah, okay, yeah, I'm gonna have to think more about whether you can actually say, define a bijection from the non-trivial irreducible representations to the irreducible components that that makes some specific choice among the various possibilities that you would get by composing with a graph automorphism.
Once we fix which node is to be left out, there's not many automorphisms left.
Yes, sorry, but there are still some automorphisms of the finite Dynkin diagram. I mean, if suppose you start with the McKay graph of type E6 tilde, so your trivial representation is here, and you know, so having decided that that's the trivial representation, you know what that representation is and what that representation is, but you've got an indeterminacy about which of those two is the right one. So I'm not sure that you can sensibly, you know, so, and then you would have a pattern of irreducible components on the geometry side corresponding to those 6 vertices. So, so sure, you can identify which is that component and which is that component, but then I'm not sure that you can necessarily say which of those 2 irreducible representations corresponds to which of those 2 components in a canonical way. Yeah, it's an interesting question, actually. I should think about that more. So next week, I'm hoping that we'll have a lecture on geometric invariant theory by Joe. Or we could possibly make some timetable changes if necessary. So we might cut back and forth between a few different topics for the next little while, but all relating to the things that have been in the lectures so far. Okay, so see you all next week.